This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Good afternoon. I'm Marianne Mason, the Dean of the Graduate Division, and I'm most pleased, along with the Graduate Council, to present Dr. David Mumford, this year's speaker in the Charles and Martha Hitchcock Lecture Series. As a condition of this bequest, this very important bequest, which we've had for many years and therefore it has become substantial, we're obligated to tell you how the endowment supporting the lectures came to UC Berkeley. It's a story that exemplifies the many ways the campus is united to the history of California and the Bay Area. Dr. Charles Hitchcock, a physician for the Army, came to San Francisco during the Gold Rush, where he opened a thriving private practice and did quite well. In 1885, Charles established a professorship here at Berkeley as an expression of his long-held interest in education. But it is his daughter, Lily Hitchcock Coit, still treasured in San Francisco for her colorful personality as well as her generosity, who greatly expanded her father's original gift to establish a professorship at UC Berkeley, making it possible for us to present a series of lectures. Just a little story about colorful Lily. When Lily was 5 years old, she was in one of the many fires that occurred in San Francisco, and she was rescued by a fire company, company number 5, and she became their unofficial mascot for many years. And then as she grew older, she actually flirted with many of the firemen and had, well, we won't go into that, but was associated with many firemen. But as her gratitude to firemen for saving her for the fire, and I guess for her continuing association, she established Coit Tower. Coit Tower, should you have ever wondered about it in San Francisco, is erected in the form of a fireman's hose. Enough of Lily. The Hitchcock Fund has become one of the most cherished endowments of the University of California, recognizing the highest distinction of scholarly thought and achievement. If you look at your program, you'll see the names of science and thought in American education and life. So thank you, Lily and Charles. And now a few words about Dr. David Mumford. As a distinguished mathematician, Dr. Mumford's achievements have been notable. He has made fundamental contributions in the study of moduli spaces of curves and algebraic varieties, yet he has always been fascinated by the processes of thought and computation as well. Bringing these emphases together over the past 2 decades, he has collaborated with computer scientists, psychologists, and neurobiologists in search of the, quote, right mathematics for describing the problems of perception. Dr. Mumford received his BA Magna Cum Laude in 1957 and his Ph.D. in 1961 from Harvard University. His most recent writings include 2 and 3-dimensional patterns of the face and Indra's pearls. He has received numerous awards, including the Field Medal, the highest honor in mathematics. This medal is crafted of gold and bears the head of Archimedes along with the famous quotation, and now I'm going to ask poor Sister Catherine, my 8th grade Latin teacher, to excuse me, transpiri suum pectus mundique potiri, which means rise above oneself and grasp the world, appropriate for all of Dr. Mumford's career and certainly a noble aspiration for all of us. And so it's my great pleasure to introduce Dr. Mumford, who is currently a university professor in the Division of Applied Mathematics at Brown University.
Thank you very much for that introduction. I'm very honored to be asked to give these lectures and a little bit daunted by it. I'm much more accustomed to addressing a professional audience, and I'm hoping not everyone here is another, I see many faces that are fellow professors, but I prepared these lectures under the assumption that indeed I was talking to an audience of non-mathematicians mathematicians, and that I should try to lay out the mathematics in only slightly technical ways, so that it would introduce and make exciting some mathematical ideas to this broader audience. This actually, I think, Professor, but you've got here for free thanks to Lily. But I have to say that as a mathematician, I'm painfully aware that mathematics is viewed as an esoteric discipline that is only vaguely connected to real life, and often in ways that are not really understood and remembered as a painful adolescent rite of passage. To me, of course, mathematics looks so different. It looks like an incredibly beautiful subject which underpins our science and technology and provides simple and elegant ways for grasping what William James called the blooming, buzzing world bombarding our senses. This is not a new thought. What's happened? Okay. Right. There we go. Back the 7th century, the Christian era, it's nice to see coming out of the Dark Ages a appreciation of number. Take away number in all things, and all things perish. Take calculation from the world, and all is enveloped in dark ignorance. Nor can he who does not know the way to reckon be distinguished from the rest of animals. So tell that to your high school students and children who are struggling with their mathematics. Okay, so my plan, there we go, is in two parts. The lectures are tied together by a couple of connections, but are generally speaking on quite different topics. So the first lecture is centered around the idea of linear versus nonlinear ways of thinking. And I want to begin this lecture by describing a little bit that I learned from a marvelous book by Alfred Crosby called The Measure of Reality, in which he makes a very convincing case as to what was really instrumental in turning Western civilization from a backward civilization in the forests of Europe to an advanced technological society that for one where, for better or for worse, totally controls the world now. So then the second lecture. So then I want to go on in the first lecture, I should say, to talk about some nonlinear things which I've been involved in in particular, a very beautiful symmetrical kind of nonlinearity, which happens to be this book, which we just published, which I thought I would take the opportunity to publicize. Okay, and in the second lecture, I want to talk about what I've been interested in more recently, trying to understand from a mathematical perspective what thinking is all about, and contrasting logical and statistical approaches to thought. All right. So around 30, it's interesting. I always thought that nothing really happened at all till the Renaissance, but it seems that already in 1300, you see. So this is Crosby's thesis, that somehow or other Europe fell in love with measuring things more accurately. That what took hold and made the difference between our route to technology and science was that they really began to measure and to use measurement in their lives. So here's the primitive. This thanks to the web. You know, the web is so fantastic. I mean, I could have spent 2 days in the library trying, but in the web I brought this up. This actually is the effective mechanism in the early clock. There's a weight wrapped around the shaft. There's going to be a heavy weight with a rope. So the shaft is trying to twist, and what happens is that toothed wheel is pressing against those two little thingies there. That one and that one, and one of them locks at a time. And so it pushes it counterclockwise first, and then it'll click to the next one will fall and break the wheel, and then it'll push it back clockwise. So the top thing will swing back and forth. And this incredibly primitive oscillating mechanism was the way people first began to do it. Towns spent the equivalent of an entire year's revenue, tax revenue, to build these things. They were hugely expensive. People were hugely proud of them, and they were good to about 15 minutes a day. Of course, people also began to measure space. So you probably in art course have seen Giotto's perspective was introduced. But in measuring the Earth, these charts appeared, and you see they use polar coordinates. There are particular points here on the coastline. So this is by the way, you see that's France and Spain coming around. There's Gibraltar down there, and there's the Mediterranean in here. So they would get the bearings. You could sail off from one spot and with every compass heading and figure out where you hit land. And so you got these overlapping polar coordinate representations, and these became the very thing for navigating then. But money is just as important to count. I mean, when it comes to counting and keeping track of things, well, they invented the whole idea of money that wasn't money, phony money, namely in banks, money of account. And they invented double-entry bookkeeping. Here's from the prince of this double-entry bookkeeping comes this marvelous description by Pacioli about how you should conduct your life. I mean, what could be more organized? He says, here's how you begin. In the name of God, on the 8th day of November, 1493 in Venice, the following is an inventory of myself, of Venice, Street of the Holy Apostles. And so he tells you what you should list, including your spices, dye-woods, and pelts in your warehouse. It was clear they liked to keep track of things. And, I mean, that's the characteristic of this. But much more. There was a whole, the scholastics proposed actually that you should measure lots of things. So heat, light, color, things that were not measured for quite a while. Certitude we will come to in the next lecture. Virtue and grace we still don't know how to measure too much. But color, Newton, I guess, was the first to measure color. But they proposed these things could be measurable. And why not? We can put a quantitative spin on all these things. So Oresme is a tremendous figure in this part of history. So in 1361, he actually invented graphing. So he actually plotted against time various quantities like position and velocity. And he understood this basic idea of calculus about the slope being the derivative. So in particular, he came across this beautiful application of the mean value theorem, that if you have uniform acceleration from one velocity to another, the result is the same as having constant average speed. This was what Galileo later on used to derive his law for falling bodies, but it was already known to Oresme. So it was an incredible period in which mathematics was really part of everyone's life, and people began to quantify everything around them that they could. Okay. But to move on, what really, I think, got our civilization going was you see, the clock was a pretty crummy clock, 15 minutes a day. And why was that? Well, there was Galileo sitting in the cathedral in Pisa, looking at this light swinging. I don't know why it was swinging, but that's what the story is. And he noticed that the period with which it swung back and forth was the same regardless of whether it was taking a big swing or a little swing. That was in my mind, the most important discovery of the whole modern science. So the idea that the period of the swinging of that pendulum did not depend on how far it was swinging. I mean, it sounds like a sort of an odd connection that you might stumble on. This is a picture of the clock that he sketched and was later built by Huygens. Huygens, it was an improvement of 2 orders of magnitude. This, you see, because so why was this? What's so great about this? Okay, there we go. So we have. So now we're making Oresme's graphs. We're making pictures just like Oresme did of position against time, and we're contrasting these two oscillators. So in the blue is basically this this Virgin folio affair that. And it would be, one would call it, I think today, a relaxation oscillator. Actually, that's Van der Poel's oscillator that's graphed. But it's kind of like the clock. You see, it moves along slowly, and then ka-chung, something is released, and bang, it gets into another state. So it's like flipping between 2 states with a sort of a slow change in the middle. And this is known to be an incredibly flexible kind of oscillation, but one subject to many parameters. So it's easy to create one, as they knew in the 14th century, but hard to really control it. Whereas the red one is this beautiful sine wave, which you see if you graph the tides coming in and out. And almost any, as Hooke realized, if you have a simple spring motion, the mathematical theory of it was really only worked out 75 years later. But I think this was a typical example of the physicist and the mathematician. The physicist got the idea. Galileo wrote his results in the form of dialogues, and there weren't any equations in them, although in many words he would describe what was happening clearly enough. But he was typical of the physicist's point of view, an intuitive, clear, elementary understanding of things. Huygens comes along and does it beautifully elegant mathematics, proves everything with classical geometry, and shows, in fact, that the way to make the pendulum really good is to make it swing against a cycloid, which corrects for the nonlinear higher-order inaccuracies of Galileo's discovery, in a way that was completely impractical. So in any case, the thing which was practical was the simple harmonic motion, which is simply the law that the acceleration of the pendulum should be the negative of the displacement. So it moves backwards, it accelerates backwards. When it moves to the right, it accelerates to the left, and that decreases the velocity and turns it back ultimately. When it moves to the right, it accelerates to the left. Right. So that has the result given by the red curve. Okay, so my contention is that we can really make a beautiful story out of this, that in many ways a very large percentage of our technology stems from this discovery. It was actually Peter Lax that pointed that out to me. He said, I said, why are you starting your calculus book with differential equations? He said, it's because the simple harmonic oscillator is the most important concept. So I believe him. So there are a couple of points. The first is simply that the future is predicted by using where you are now and your rate of change. You see, so here it was back there, acceleration proportional to displacement. So you know where you are, you know your velocity. That predicts the acceleration, it predicts the rate of change of your velocity determines the rate of change of your position. So okay, it's a differential equation. But better than that, it has this magnificent property, and this was Galileo's discovery. If you increase the swing, f of t, it doesn't change the shape of the curve or the period. So if an oscillation of one size solves the equation, we double it, it still solves the same equation. And if f and t solve it, so does their sum. So that's what linearity is all about. Now, why is it important? Well, it's the only reason you can hear everybody talk in a cocktail party. Because what's happening? In a cocktail party, everybody's voice is being superimposed on top of everybody else. And in the air, these are basically simple harmonic oscillations with different frequencies. They're combining linearly, and your ear is then decoding them by using the fact that they are a linear superposition. And you then can separate out the different harmonics. You get formants for vowels. You get the characteristics of different voices, and you hear who's talking to you. It is also the reason you can buy a frequency. I mean, the Aborigines and the original Americans thought it was bizarre that Western Europeans thought they could own land. Well, what's more bizarre than owning a frequency? But why can you sell a frequency? It's precisely because in the ether around us, there is a linear superposition of every signal being put out everywhere in the world. You can combine them linearly, and you can take them apart linearly. They're all there. They do not interfere with each other. But even more than that, I think one of the most astonishing ideas of linearity is the idea of Schrödinger, that you can have a cat in a box, which is with 50% chance, which is a superposition of a dead cat and a live cat. All you do is you turn your back and you trigger a little needle to some bit of radiation, some subatomic event controlled by quantum mechanics. And that event subatomically is a linear superposition of two things happening. And when the needle kills the cat is then in a linear superposition of being dead and alive. It's a very weird thing, but quantum mechanics says that the world itself is linear. We can add a dead cat and a live cat and create a state of the world. Whether this will ever impact our lives is not clear, but with quantum computing, it just might. Here's some linearity from my boat this summer. It's kind of beautiful to see such a good approximation to sine waves. A very still night, but with this beautiful ripple. And this is actually a superposition, again, of ripples with slightly different angles, causing these sort of dead spots in it, like here. You see where they cancel each other out, and other cases where they double. So it's a nice linear superposition in water waves. Then, however, we have not stayed in the linear world, so some very you can argue, you can go back to many things, but certainly one very seminal event happened in 1834. So John Scott Russell, who was a British scientist, was riding one day. So this is the quote from him. "I was observing the motion of a boat, which was drawn rapidly along a narrow channel, when the boat suddenly stopped. Not so the mass of water in the channel, which it had put into motion, assuming the form of a large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued along its course, apparently without change of form or diminution of speed. I followed it on horseback and overtook it, still rolling along at 8 or 9 miles an hour." They're called solitons, in fact, to this day, from this solitary elevation, these waves. These are not linear waves. If you double their height, they go faster. So they absolutely disobey. You can, to some extent, superimpose them, although they interact strongly when they collide with each other. But if you're lucky, they come out the far side still intact. He was a Scotsman. So in his honor, the Scots recreated his wave here. So there's the canal over there that they chose this. There we go. This beautiful straight stretch with uniform bottom and so on. And here is the solitary hump of water. It's hard to see because the light's reflected in it, but you can see the profile. It's coming up to the edge of the dock. And it's come here. They're chasing it from behind instead of on a horse. I don't know why they didn't get a horse, but it's rolling along, and you can see how everyone is beautifully amazed by this. Now, interestingly enough, it has displaced the linear principles now. And when you talk across the ocean and so on fiber optics, the signals are sent precisely using these solitary waves. Because you can do this at such an unbelievably high frequency. I mean, the advantage of you want to get to very high frequencies, so you can pack more bits in, and this has turned out to be this discrete form of sending pulses in the form of these solitary waves has turned out to be a much more efficient way of sending messages long distances. Now, so nonlinearity is really today omnipresent in people's study of virtually every applied mathematics and pure mathematics. I just, again, thanks to the wonders of the web, pulled off a random conference that happened recently that was nice to post some of the illustrations in the conference. So you have these nonlinear effects in water here and here, nonlinear effects in sand, nonlinear effects in the flow of drainage and the interaction of the soil and the water. It's quite common that you get in these effects these repetitive patterns, but often patterns that repeat with varying scale, as shown here, and patterns which take advantage of the complexities of space. So one of the real intrinsic nature of our space is this possibility of spirals. And the nonlinear effects produce these in spades. Now, what is really, in some way, the origin of these nonlinear ideas? The origin of these ideas is basically that you do something relatively simple to something, but something which is not linear, which involves some sort of twisting and folding, and you repeat it many times. So if you can take almost any nonlinear transformation and repeat it many times, and amazing things will happen. So one of these nonlinear effects which has been studied is what's called the Baker's transformation. It means you take a piece of dough, you squash it flat, and you fold it over in itself. So you do that many, many times, and you create phyllo pastry, and you put a little butter in between. It tastes good. But that's, with apologies, this is Nancy Capel. It's a shame. I actually never asked her permission. But we happen to have this database of images. And so we're going to show you what happens with the Baker's transformation. We're going to squash this. So imagine that all this is a pattern in the dough. We're going to, from the top, squash it halfway down, and then we're going to twist it and bend it around on top of itself. So that's what's happened. So you can still see her face here, her eye and her mouth. Her hair is twisting, at the top is twisting around. But now we're going to take this, we're going to squash it down a second time and fold it up. So notice, I wonder, you see, what's going to happen to her chin here? So that's down here. Having gone from from here to here. When we do this a second time, you see, this will be squashed down, and this line here is going to go over here. So let's have a look. There, you see, so her face is over there. Notice some parts of it, however, are quite intact. That eye is there. other parts are being stretched. So in here, we're stretching hugely in this direction, and we're compressing in this direction. We're compressing many layers, which actually have come from different parts of the image here, together. So you repeat this, and it's interesting. You can still see bits and pieces. That eye has a tendency to persist. I think this has pretty much destroyed anything recognizable in the face at this point. And this goes on. Right. Oh, look at that. I have not, by the way, this is only the second PowerPoint lecture I ever gave, so I've made a little blunder here. I see the second comment there. The key point in this kneading technique for the dough is that you're squashing it in one direction and stretching it in another direction. So this is known as Lyapunov exponents. Some differences decrease. So in some ways, two systems which were dissimilar get closer when you do something nonlinear because you've squashed the difference between them, but other differences get expanded. And so this has been known as the butterfly effect in weather, that if a butterfly flaps its wings in one part of the world, it may cause tornadoes in another part of the world. It's perfectly, although I don't know if that's ever been, weather is a tricky thing. I mean, in that it's semi-predictable. But in any case, this sort of system has this effect that tiny differences in where you start can magnify hugely after a certain amount of time goes by. So this is characteristic of this nonlinear world. Now, one would say that the nonlinear world is, it seems as if all bets are off. We now have such a gigantic amount of things that can happen. Are there any organizing principles that help you see some pattern and perhaps beauty in this nonlinear world? So there is another organizing principle. Now, linearity has this basic property that any smooth object, if you look at it under the microscope, if it's a smooth piece of steel, of course you get down to the atomic level and it's not smooth. But let's assume that mathematicians had control of the world and they could make smooth things, truly smooth things. They would have the property that when you look at them under a scanning electron microscope, they would not only look smooth, they would look flat. Because a smooth thing, the closer you get to it, it just begins to look flatter and flatter and flatter. Now, this property of their getting more and more linear under magnification, why not twist it around and say, imagine that there is some aspect of complexity which repeats itself when you look more and more closely at it. So no matter how closely, you still find intricate structure. All right, so that's certainly characteristic of our world, as the beautiful book Powers of 10 of Philip Morrison and his collaborator showed, where you see the universe over, I don't know, some 50 powers of 10. You see complexity on almost every scale. But there's, in that case, this complexity is perhaps not so easy to describe. There's a possibility of something which is describable. Namely, suppose it happens that when you blow it up and you look at the complexity in tiny parts of it, that what you see is similar to what you saw in the whole. That the small parts have the similar structure to the entire whole. So it was popularized by Mandelbrot, but has occurred in many applications of science. It actually was observed in biology in this doggerel of Jonathan Swift. So naturalists observe a flea hath smaller fleas than on him prey, and these hath smaller fleas to bite him, and so proceed ad infinitum. So I don't think there's a better expression of self-similarity in the biological world. I'm not quite sure what, is that 19th century? No, it must be 19th century, because there were no microscopes, right? Anyway. However, this notion of self-similarity, and now I have to apologize if this offends anybody, but there's a religious aspect to self-similarity, which actually I wasn't that aware of until my co-author Carolyn Series pointed it out, and it was so totally convincing. That this self-similarity is exactly the essence, one of the essential core ideas of Buddhism. I don't know, Hinayana or Mahayana, anyway, the trend that went through Tibet and China. So here in the words of Charles Eliot is this expression of this notion in Buddhism. Every object in the world is not merely itself, but involves every other object and in fact is everything else. So the idea was a single hair from your head in a certain profound sense, is you. Leaving aside the spiritual aspect of that, it is asserting, on a certain level, an incredibly strong self-similarity in the world. And for that reason, when we wrote our book, we called it after Indra, who although it was originally a Vedic god, was adopted by the Buddhists and has this magnificent metaphor associated to him. Indra was the god of thunder originally, and in the Veda, god of the sky. So in the heaven of the great god Indra is said to be a vast and shimmering net, finer than a spider's web, stretching to the outermost reaches of space. Strung at each intersection of its diaphanous threads is a reflecting pearl. In the glistening surface of each pearl are reflected all the other pearls, even those in the furthest reaches of heaven. In each reflection, again, are reflected all the infinitely many other pearls, so that reflections of reflections continue without end. So this I put to you is exactly a description of what Felix Klein discovered some 120 years ago and called Kleinian groups. And here is one of these depicted. So I'm cheating a little bit, so I don't know if anyone will catch me on this, but you can see there are these. Wait a minute. Now how does it work? Yeah. Okay. So there are 6 large red pearls here, there, and then the 3 in the middle here, and reflected, for instance, in this pearl, you can see. I'm colorblind, so I'm not going to name. Is that green? Whatever it is, there are 1, 2, 3, 4, 5 of them, the reflections of the other 5 in the 6th. And now you look, for instance, in this pearl, and I'm going to lose track, because these are the first order reflections, these are the second order, these are the third order reflections. So if we count these guys, I'm not going to try to do it here, but wait a minute now. So right, so we should have in here, yeah. So we have 5 of these guys, and reflected in each of these are going to be yeah. You see, right. So I should have the 5 reflections in here. Anyway, reflected. It should work out. It'll work out better in the next one, which is easier to comprehend. Okay. The main point is that Klein came across a mathematical situation in which this infinite iterations of a very simple family of nonlinear maps came up in an extremely natural way. Now, to contrast this, I want to make one important distinction here. So if we go back, here we have the self-similarity of the small parts can be of 2 kinds. It can be statistical or asymptotic. In the case of smooth things, it becomes asymptotically a straight line, and it's exactly the same as itself. But in finite levels, it's only approximately similar to what it started with. You can have statistical things like clouds, which have every detail is different, but when you zoom in on them, they have exactly the same statistics. We're dealing here with I'm hitting the wrong one. Self-similarity of an exact form. exact under a nonlinear transformation. So there is a key nonlinear transformation behind it. And this was Klein's original PhD thesis, basically, his synthesis of geometry, was that geometry consists in the study of congruences, and congruent things don't have to be identical, they just have to have certain properties that are the same. So the same can be with respect to certain transformations. And interestingly enough, Klein's famous Erlanger program, and this is again an observation of Carolyn's series, was Lewis Carroll's Hunting of the Snark came out about 5 years after, and of course Carroll was a mathematician, as you know, about 5 years after Klein's speech. And I would say it's quite reasonable, her hypothesis, that Carroll had knew Klein, and this particular part of Hunting of the Snark is taken from Klein, because it's a beautiful poetic embodiment of Klein's idea. You boil it in sawdust, you salt it in glue, you condense it with locust and tape, still keeping one principal object in view to preserve its symmetrical shape. So here's a little illustration of it. No, wait, there it goes. Okay. So this is Dr. Stickler, we call him. So he is being moved along by this nonlinear spiraling motion with his feet on what I think might be a green line and his head on a red line. And he's being sucked into this so-called attractive fixed point as time goes on. And then in a second, he's going to go backwards, too. So he has an infinite trajectory. He is simply there to show you the motion, which is going to be embodied. So here he is. You can see the nonlinear distortions are huge, but incidentally, every angle in him is the same. The angle in the crook of his arms, if you measure it, is going to be identical here as it is here, even though the head, of course, relative to his feet, is like Greenland in a Mercator projection, which also preserves angles. Okay, so this is the basic ingredient for Klein's work. Oh, darn, what's happening? So I have to give credit here to my second co-author, that is Dave Wright, who is a genius at doing these things, and we're going to see a series of MPEGs. He's just in the last couple of weeks, because of these talks, has been putting these ideas of these Kleinian groups in MPEGs. So there are two parameters in here I want to mention. The speed at which Dr. Stickler moves can be varied, and the amount of spiraling that he does in order to get closer to the attractive and repulsive fixed point can be varied. So there are two parameters forming one complex number, which underlie each of these basic symmetry motions. Okay, now what Klein started with and what produces this interesting interaction of symmetry and chaos is that he had, suppose you have two motions at once that you're trying to track. So we have the original guy here, and one transformation is going to move him along this whole path. This is a slowpoke, this guy. It moves him. There's no spiraling in this picture. It moves him simply from this repulsive fixed point to that attractive fixed point, so that he has a steady motion here. This other guy has 7-league boots and moves him in one step to there, and in the second step he's already too small to resolve. He's way back in that cluster there. And if you go backwards, he came from here and from down there. Now, the point is that you can combine the two transformations. So if you first do this guy and move him backwards and forwards here, you have this, and now we take that whole collection of Dr. Stickler's and move him by this motion, you get this whole chain of guys. And you move him another time and you get a whole chain of guys which is in here. Or you can do it in the other order. Now, it's a little sparse to see, but if we take this is another one of his trajectories from there to there to there to there to there, and we move that by this transformation. It now becomes a trajectory from in here to here to here, and the rest are invisible. And we apply this transformation a second time, and it goes from here to here to here. So, so we have what's called a free group here on two generators. There's a tremendous number of places he can go. And as Bill Thurston and others have remarked, if you wander around on walks like this, you better take Ariadne's thread with you, or you're pretty darn likely to get lost. There are so many, because as you go, you can, you see the problem is that if you take motion A and motion B, you get to a different place from taking motion B and motion A. And so if you take motion A and motion B and you try to go backwards by first reversing motion B and then reversing motion A, you're not going to get back to where you started. So this is, the Dr. Sticklets form a tree here. You can make a tree out of this whole thing. These arrows, you can see that the arrows, this is one branch of the tree and another branch goes this way. But you see we can go from here to here, or from here to here. There's a tree with 4 branches in the middle, and at every intersection it has 3 branches that go out. So from here there are 3 ways to go forward and 1 way to go back. You can see that that's a pretty difficult maze. If you're gonna, you need to just write down how you got there. Okay, now what I wanted to say, when we did this about 25 years ago, we plotted these pictures, and we had this incredibly primitive equipment, this so-called Tektronix terminal, which was state-of-the-art sort of thing. And we had this flickering green light that went across it and traced these graphics. We had the idea, let's do this. Let's take these transformations S and T and look at all the places which you can get to and see what they look like. That's what's called the limit point set. The limit point set is a thing which is mapped to itself by both S and T. The way you should think about this, the way I think about it, is that S and T, it's like a marriage. You have 2 people that have different ways of moving, and they try to get together, and sometimes they form a marriage which is a relatively cool marriage. They keep up their own paths and they don't bump into each other very much. Sometimes they have a marriage which gets really complex and baroque, and they interact in incredibly complex ways, and the picture gets complicated. Other times, what they do together is so totally chaotic that they get divorced. And what's happening here, we're going to find exactly this in mathematics. The 2 transformations S and T, they can do very simple things together, but they can interact in complex ways and produce things which look like those fractal patterns that we often observe in nature. And these can get more and more complicated. So, okay. So here's the case where they keep each other at arm's length. Okay. So we're tracing this tree. Now the nice thing about this tree is that there's a natural direction in which we can traverse it. Now these circles are like the original pearls, and moving down through a series of the pearls, you get to one of the limit points. You have a reflection of a reflection. It's not really a reflection, so that's where I'm cheating. But you get to the ultimate limit point. But now, what we want is that the 2 transformations are a little more intimate with each other. And so we ask that they touch each other now. And now when they touch each other, those limit points, instead of being like an isolated set of little islands that they can get to, become a continuous curve. It's basically a circle which is tremendously crinkled in itself. And as we're going to see in a little while, we could have illustrated it earlier on, but the illustration is more powerful in a second. We're going to zoom in to this limit, so-called limit point set, and we're going to see that it exhibits this exact self-similarity. Why is it self-similar? It's because this glowing curve here has the property that both S and T take it to itself. And S and T are maps which do a tremendous amount of expanding and shrinking. So the big features of that curve are going to be repeated endlessly in the smaller features. Okay. Yes, here we go. So at this point, when this is going to trace this curve, so now we're putting spirals in. We had no spirals in the previous thing. We just let them kiss. But now they're both kissing and spiraling. And in fact, the circles can't even be drawn in this situation. When this curve finishes, we're going to take a telescope, a microscope, and we're going to zoom in on the thing. So notice the features it has. Basically, it's dominated by this big curlicue because one of the transformations does exactly that. Now, we zoom into this part of the picture, and we see that it has the same shape completely. We zoom in again to another part of the picture, and it still has the same shape. We zoom in again, and they ran out of patience. We could have zoomed 10 times, actually, straining the floating point resources of the computer. But you can see that this has precisely this fact. It has exact self-similarity. In what sense is it exact? It's exact in the sense that this spiral, we could find one of this very small family of what are called Möbius transformations, which would make this spiral look precisely like the spiral of the original curve that we started with. Everything repeats itself endlessly. Another beautiful thing can happen in this situation. There we go. So a new kind of symmetry is present in this picture. So now notice that these circles, so we have a repetition of this circle and that circle and this circle and this circle and this circle and so on down to here. And when this is finished, we're going to come up from the far side. And so what you're going to find is that there is now a new kind of symmetry which you can see, condense it in sawdust and boil it in glue is it's not bad. It kind of looks like. This chain of circles is an infinite chain starting here and going out and coming around again. And a second infinite chain goes the other direction. And the beautiful thing is that you can put both chains together and produce a picture which has both symmetries simultaneously. In fact, this picture can be produced if you start with this big circle and those two circles there. You can produce the picture by looking at the inscribed circle between these three here. Well, there are actually two. This is equally an inscribed circle between these three. And then you go on and put an inscribed circle between these three, that's that. An inscribed circle between these three, and that's that. Between these three, and that's that. You continue putting inscribed circles everywhere, and you generate this sort of foam. So this is characteristic of another kind of symmetry. Okay. Now this guy. So I mean, you get a little bit carried away by this. I hope you share my enthusiasm for this. Watching these is because the dynamic aspect of it makes you think, my God, what an amazing dynamic can produce something so elaborate. So notice we're really tracing what mathematicians call it's almost a simple closed curve. It never crosses itself. It touches itself from time to time, but we never lift our pen from the page, and we get a curve like this. So this is a situation where we have a combination of spiraling and the so-called parabolic transformations. And if you were to move it backwards to its original incarnation as a curve with an interior and an exterior, you would find that half of these circles are inside the original curve and half are outside. And the curve has collapsed in such a way that both its inside has become a union of circles and its outside has become a union of circles. So let's see, Alan, I'm going to need your help. Let's see, are we coming to the next one? So now we're, well, you know, we've got to switch from Bill Gates. Don't worry, don't hurry, because right, this crashed PowerPoint, and so, but QuickTime came to our rescue. Right, now click on figure 8 parts lower. What? No, where are you? You've got to click. You've got to bring it down. Yeah, that's it. Right. Click on that. There we go. Okay. No, don't do that. Just leave it. Now go and click on this down here. That'll start it. Whoops. I'm sorry that I forgot to rewind the movie. Darn it. So you saw the punchline. So the point is, so here is a marriage in which the couple has decided to try out everything. Sorry, these metaphors are getting better in some people here, I can see. For a long time in the 19th century, there was a controversy. Could you get a continuous mapping of a circle into the plane or into the two-dimensional sphere, which moved around in such an irregular way that it touched every single point in the plane? Those are known as piano curves, and they indeed exist. They were first made rather artificially, and little did Felix Klein know, I think, maybe he knew, I'm not sure, that he had these piano curves under his thumb in his constructions. So this guy is so busy, he has this wild, crazy scheme of his own. I mean, you can think, how does this moving point know? And you might say he's forgotten a few places, like here and here. Well, he didn't, actually. That was our computer that ran out of steam. If our computer didn't run out of steam, those little filigrees would have come in and curved into there in circles, and these would have curved in, and this actually would have been completely filled in. So this would fill in the entire plane. If, as I say, our computer had been a little stronger. Just to sort of, put a few buzzwords on it, it's known. Just to tell you how mathematics can have these incredible connections with itself. Believe it or not, this thing is is related to knots you can make out of string. One of the simplest knots you can make out of string is what's called a figure 8. And that figure 8 knot is connected to this in the following way. That curve is filling the plane, and so, but you imagine the plane wrapped around a ball, so that it comes around and has one point at infinity, which at one point this curve will touch, that point at infinity. But now you let these S and T's, these symmetry maps, act on the inside of the ball, which they can do. They move the inside of the ball around. We take the way they move the inside of the ball around, and we identify every point with where it goes under S and T. Another way of thinking of it is you take the inside of the ball and you cut out of it a sort of a heart, which has the property. It's like that place that Dr. Stickler was sitting. It moves to places disjoint from itself under S and T. You glue it together, and you get a three-manifold, which is exactly the complement of the figure 8 knot. Anyway, whatever that means. Now, Ellen, could you click on the background? Are you still there? Click on the background there once, and now go down and click on the little slidey thing, and we'll get back to PowerPoint. A little to the left. Beautiful. Yeah, right there. Yeah. Okay. So I've one last. Yeah, click. What? Why doesn't that work? You should click. Ah, there it goes. Okay, beautiful, beautiful. Thank you. All done. Thank you very much. That was perfect. Okay, right. So we have this beautiful thing, a piano curve. So it's this is sort of like a piano curve found in nature, as opposed to these artificial ones of the 19th century that were obviously very man-made and very sort of like buildings going left and right and everything. This one is. Okay, so a last point. There were these parameters in the groups that tell you whether S and T are really, to what extent they're interacting with each other and whether they're causing chaos. So I should say that you can look at all the parameters in S and T, and what you find is there's a region in those parameters in which S and T really produce total chaos. Probably there are some patterns there, but it's not obvious what patterns what sense you can make of them. Then you have the S and T's which are moderately connected to each other, and those that are right on the edge of the chaotic space. So another thing you can do, which is kind of fun, is you can imagine taking a flyby in the space of parameters. So we now are going to look at the limit set produced by the transformations, but we're going to vary the parameters in the two transformations and make a movie which shows how the limit set varies as the parameters vary. And this really blew us away when we first saw it. There we go. So what we're doing is we are moving in what's called trace space here along a certain trajectory so that the limit set develops. You see what's happening here. Let's do it again. I think I'm just going to do it again if I do this now. Yeah. Notice that the spiraling comes and goes, you see. At certain points, and the spiraling comes in complicated patterns. If we get closer to the boundary, it's even more impressive, but we weren't able to get it done in time for this lecture. But what's happening is that you're moving towards situations in which these transformations are acquiring a tremendous amount of spiraling, and then you move away to the places where it's more rectilinear. And all of this has encoded in it a beautiful sort of numerology having to do with rational numbers. So, that's as much as I wanted to say. I wanted to say that we wrote this book with a goal in mind, and it was when we did this mathematics. It wasn't really mathematics. What we did was to realize that we could implement mathematics in computer graphics and make tangible mathematics that Felix Klein had done. And what occurred to us was that this was a piece of mathematics which is really very easy to explain. Well, it's relatively easy compared to almost all other kinds of mathematics. Namely, all you need to do to really understand this, you need to know about complex numbers, because complex numbers are inherent in the formula for this spiral. Although even for that you could skip if you just want to know the geometric effect of them. But you need to understand what this idea of looking at symmetry in terms of repeating two transformations S and T in various orders and where you get to. And then you need to combine them in this fundamental class of spiral motions. And then all you need to do is play. So we wrote the book with the idea that it was something that, for instance, a bright high school student, any computer hobbyist who likes to program for his or herself could easily read. To say that there are certain things, I mean, there are questions we could easily raise here which are really on the frontier of mathematics, which have not been solved. But the book tries to show that a big chunk of this is not in any sense as complicated as the proof of Fermat's last theorem, for instance. Thank you.
Thank you, Professor Mumford. Professor Mumford has graciously agreed to answer some questions. So if you have a question, if you'd like to come to the microphone.
How do you want to do it?
Okay, stand up there if that's okay, please. Yes. Don't be shy. Come to the microphone. You made it so stunningly clear that there are no questions.
Jerry, you've got to ask a question.
Good.
You'll embarrass me if you don't.
I have a real layman's question now.
Yeah, good. That's what I want.
I don't quite understand the relationship of the stick figure to the reflections of the pearl. And it seemed like you have combined them. I mean, they look like the...
Yeah. Okay, I know. That was, that's true. That was slightly confusing. You see, if you reflect twice in a mirror, it's actually seeing yourself you see, in a reflection, you reverse left and right. But if you reflect twice, it doesn't reverse left and right, and you get one of these motions like S and T. So what we're doing is not simply taking reflections upon reflections. What we're doing is we're taking these transformations S and T, and we're repeating, following one S with a second. Yeah, maybe I can go back for a second, make it clear. There we go, that was it. There, okay. So you can think of what's happening here, that you start with this guy, and it's not that we're reflecting him and seeing the reflection of the reflection in here. We're simply moving him forwards by S, arbitrarily many times, and backwards by S, and forwards by T, and backwards by T. Now you can connect this to reflections. If you start with a collection of reflections, we can follow one reflection by another reflection, and take those pairs, and we get mappings like S and T, and you can get an exact correspondence between them. But I agree that the link, as I've explained it, was not exact.
What might some applications of this be to science or technology?
Yeah, that's a good question, as they say. It's of course amazing when you find a piece of mathematics that comes really out of algebra and geometry, that has a really immediate relevance to the real world. I don't actually know of this. This is really a piece of pure mathematics. So I'm afraid to say that, you see, what certainly the idea of self-similarity is something which is present in thousands of areas of applied mathematics in investigating the effects of nonlinear things in the world. What this mathematics has done is it's taken this idea of nonlinearity and it's idealized it in this pure geometric setting, where, as far as I know, it does not actually have. Maybe I'm wrong. Am I wrong? Any mathematician want to contradict me? I don't know of any application. And you have to live with that. Sometimes the math connects, sometimes it doesn't. I mean, who would have thought prime numbers were going to connect to the real world until they discovered this encryption algorithm using prime numbers? So this is the piece of math waiting for its application. Tomorrow I will tell you more about things that really are full of applications.
So I was wondering, if you look at the self-similarity in a continuous space,
yes,
you expect to find infinitely many levels of self-similarity. That is...
Yes.
But if you look in a discrete or even finite space, you'll expect to find only finitely many levels of self-similarity. Now, we can then pose the question, in the physical universe, which case do we find ourselves in? I think it's the latter, isn't it?
The latter being the continuous, or the discrete. Oh, you think it's the discrete?
Because,
no, I think both occur.
Because we, even if you look with two opposite mirrors...
Yes. Oh, okay.
Because of the fact that you have atoms...
Right. Yes. Yes.
So you really don't have infinitely many levels.
Yeah. So I think the answer to the question is that when we said we would look at self-similarity which was geometrically exact,
right,
then we pretty much restricted ourselves to something which was discrete, because a continuous group of symmetries really only leaves you very elementary shaped objects. We need a discrete group of symmetries to get really complicated objects. But if you instead look at statistical self-similarity, which is going to arise tomorrow in one example, you then find that there is a you can easily have self-similarity under a continuous infinite group. So, for example, you can scale by an arbitrary factor and get statistical self-similarity. And that does occur indeed in the real world. I mean, so-called conformal field theory in quantum mechanics is, yes?
What does it mean to say that it occurs with infinitely many levels of...
Well, you see, it's not that self-similarity of one ideal rigid object under these transformations. A statistical self-similarity means you have a family of similar-looking things, like clouds. And you can take a cloud and you can magnify it by any factor you want, and then you can take certain statistics, like correlation functions of whether it's cloud here or sky here. I'm thinking of things like clouds which, I mean, some clouds, of course, are different, but which have fine structure. And so you can measure a statistic of the texture of that cloud, and you'll find that statistic is the same when you blow up the cloud. I mean, Mandelbrot has many instances where he looks at the coastlines of, so you could, instead of these curves here, we can have the coastline of some place in the world. We blow it up by a certain factor, and we measure similar geometric properties of it, and we find the statistics are the same. So the details are different.
They're the same over many orders of magnitude,
yes.
But you get to the level of atoms. And then
all right, that's, okay. That's a reasonable point. So, of course, when we get to the atomic level, but we could have, we can imagine models of the world in which we have continuous statistical symmetries at every conceivable scale. I mean, like, we can idealize it. Now, we come to how well that model applies to the world. The symmetry still doesn't have rigid levels. It isn't like level 1, level 2, level 3. It's a smooth series of levels, but it breaks down when you've gone a certain number of orders of magnitude. Yeah, so that's a very good point.
Well, if there are no more questions, we want to again thank you for a really stimulating presentation.